Hi, am I audible or?
Does it work?
Yeah. Okay. Hi. So I'm Subhayan. I just finished my 4th year of PhD in the Multimedia Research Center at University of Alberta, and I'm going to present a paper that I presented at IEEE Census last year. So it's like a remote sensing application. So using both computer vision and machine learning techniques for a remote sensing application, I thought it would be of interest to the general audience. So the specific thing that we are working on is a technology called InSAR. So the full form is the Interferometric Synthetic Aperture Radar. So it's a way that you can use satellite images for measuring ground movements. So the application that we are exactly interested in is in case of mining sites, because of the mining operations, because of the excavations that happen as a result of the mining operations, there are the risk of landslides. Now, you can use satellite images for comparing like two images of the same mining site taken at a difference of, let's say, 1 or 2 weeks. And then if you take a sort of difference of those images, you can quantify how much the ground has moved. So it may be like it's the ground is coming up or coming down. And if the rate of motion is beyond like a certain threshold, there's the risk of landslides, and people working in the mines may be of danger. So we want to raise an alarm. So mostly as of now, like this type of techniques are of interest to mining companies, but in the future, we can even use this type of techniques for monitoring pipelines, like pipelines that carry oil or natural gas that run along like different provinces. So in that case, you would be monitoring something that's like across thousands of kilometers. So the existing vision-based methods are slightly slow in that respect because of the amount of data that you have. And that's why the some companies that work in this domain are looking to go towards GPU acceleration, machine learning, this sort of things. So the challenges in here arise from the fact that when you have a satellite image, it's almost impossible to get a clean satellite image. So the existing methods of denoising that are there in the literature, they mostly work for real image, like optical images. So in case of optical images, it's relatively easy to get a clean optical image, and then you can add noise to it, and then you can train a network to remove the noise. But in this kind of applications, this is a bit difficult because of the lack of clean satellite images. And the reason that images are not clean is because the microwaves that are used for measuring this kind of ground movements when they pass through the atmosphere, because of different type of factors like turbulence, atmospheric moisture, the phase gets contaminated. So that's why you end up getting an image that has a lot of different components in it, and a lot of it is noise. And also the other thing is, like, most of the denoising literature that you see are working for the real, the optical images which are in the real domain. So it's, you might have like 3 channels RGB, but those are still real numbers. But the microwave signals and the way they capture it, the signals are in the complex domain. So there's like a wrapped phase. And the last thing is that when you capture an image and you actually end up removing the distortions from it, it's, in case of like optical images, it's enough if you just give it like a clean image. But in the case of microwave images, like there's usually a processing pipeline. So the very first stages of the pipeline might deal with registering 2 images. Like I said, that a satellite takes multiple images of the same place, but the images are not registered with each other. So the first stages may be that you need to register it, and then after a few phases, you get to the point where you remove the noise from it. And then in the subsequent phases, I said like it's a wrapped signal, so you need to unwrap it. And then in the final stages, you actually end up calculating the motions. So when you are doing the denoising step, so when I denoise a pixel, I also have to output a number known as the coherence. So the coherence is sort of a confidence measure that says that, okay, I am this much confident about the value of this pixel, about the value of this denoised pixel. So that can let the later stages of the pipeline know that how much reliable that pixel is. So if the pixel is not reliable, the subsequent stages would ignore it or take that into account. So this is an example of a typical InSAR image, and it's captured using the CSAT satellite that you can see there. So this is an example of a volcano, the Hawaii volcano. So this image, like I said, it has 2 parts, because it's a complex number, it has phase and amplitude. So this is the amplitude part, and the amplitude part looks, you can somewhat think of it as an optical image, because the amplitude of a point on the ground depends on the type, mainly depends on the type of reflector that is there on the ground. And the other part is the phase. And when I say that I want to detect the ground movements, mostly the thing that I'm looking for is the phase. So the phase at any point gives me the distance of that point from the satellite. So because this is a wrapped phase, so usually there's like an ambiguity. So because it's like modulo 2 pi, so it's n 2 pi plus something. So that's why you see this kind of interferometric fringes. So these fringes appear when I like subtract two images, and usually when I do some denoising of this kind of image, the ultimate aim is not to get a perfectly clean image. So I want to recover as much information from those points where it's still possible to recover something. If something is completely noisy, I can ignore that. But I should output a coherence that is reliable enough. So the coherence should tell me that this part is not reliable. So I don't really care what the filtering output is for that part. So like if you look at the earlier works, so this thing I think started around the 1990s. So the earliest method is a boxcar filter. It does exactly what it says. But the main problem is that it like suffers from overfiltering. So you have to select the like size of the sliding window and all. So the later methods can be broadly classified as spatial methods. It starts with the Lie filter, and there are subsequent improvements of the Lie filter, and there are the frequency-based methods which start with the Goldstein filter and the subsequent improvements of that. So enhancements of the Lie filter mostly adapt the denoising to the local fringe structure. So the fringe is the kind of like bands of colors that you saw in the earlier slide. So it adapts itself to the fringe structure, so it denoises accordingly, like increases the or decreases the strength of the filter. And then the modifications of the Goldstein mostly look at the coherence and adapt itself to the coherence, so that if something is very incoherent, it can still overfilter it, but if something is not, it does the other way around. So the more recent works that you see in this area, basically there are three categories. I mean, there are some neural network based methods that do despeckling of SAR images. So SAR image is something that has just the amplitude, so I'm not doing the interferometry there, I'm not subtracting the images. The second is like you could have methods that improve the geolocalization accuracy for like the optical satellite images. And the most important thing is that at the time that I started this research, there weren't really any CNN based methods that try to either denoise it or classify the coherence. So that's why we thought of like starting the investigation, and I'm sure like as of now there might be at most like one or two methods that do exactly this. So then like because this is a machine learning problem, the first is like how do we get the training data. So the thing is when we have to acquire the training data for this kind of applications, we have to get it from satellites. So we were working with a company in Vancouver, 3V Geomatics, and they acquired the images for us, and then we have some real data that we can investigate. And the other way is that you could build a simulator that simulates the kind of ground movements that you can expect. So in that case, you have something like a relatively clean ground truth, but then you can make a simulator only so close as the real thing. There will always be like some difference. So that's for the like the starting point, like the data. And then, so for calculating the coherence, obviously, like we need two images, and a coherence is a sort of a correlation measure between like two images. So if 2 points are having similar values, you have a higher value of coherence, and like vice versa. So first we designed a CNN, and this actually is yet another paper, but I don't have time to go into the details of that paper. So this is, I'm giving like a broad, general overview of how you like we built a CNN for denoising an InSAR image. So it's relatively simple. Like you can imagine an autoencoder structure. So it goes from a higher dimensional image, progressively it like subsamples it to a lower dimension, and then it tries to get back to the higher dimension. So the idea is that it learns only the essential features required to reconstruct the image, because we are putting a bottleneck on the dimensionality. So in that process, it learns to reconstruct the real image, I mean the actual image, as not the noise. So this is like a broad description of that, a very short description of that. So the way that we create the training data is that we use that denoising network to denoise a bunch of images, and then we calculate something called the raw coherence. I'll show you in an example what the raw coherence means. But in reality, it's like just a 7x7 like sliding window, and then you have a formula for calculating this. I'll show you in the next slide. But the raw coherence itself is extremely grainy, and it's not really that useful. So we do the MRF-based thresholding on that raw coherence for getting the, because you know in MRF-based method you need something like a prior or initial estimate, and then it like improves that based on iterations. So for getting that initial estimate, we perform like the third step that we see here. And for like setting the initial threshold, we use the Orthu's method, and it like determines the initial threshold. Yeah. So then finally, using the MRF, we improve that initial estimate. So this is the like the formula for calculating the raw coherence, and it's like obviously because it's in the complex domain, so it's like a correlation in the complex domain. You could think of it like that. And then followed by the MRF thresholding. So P is the prior and S is the pixel. So the first term makes sure that it's not really far from the prior, and the second term is the smoothness constant. So each pixel should be smooth compared to its neighborhood. And then alpha is the term that like controls the amount of smoothness. So this is for creating the training data, and then what you have is another network that actually does the classification. So we use separable convolutions to reduce the number of weights to be trained. So separable as in separable depth-wise. And the reason that we did all this is because like we don't have like a lot of real training data. So if we wanted to make a network that doesn't have too many weights, because the more number of weights you need to train, the more number of training data you need. So that's why we wanted to cut down. We wanted to have a network architecture that's as simple as possible and still does the job well. So the output of the last convolutional layer is like basically classifying each pixel as the coherence amplitude, and that's why it's the sigmoid output, and the other activations are ReLU. And we like minimize the binary, the cross entropy between the output channel and the training target. So for the implementation, we used Keras with TensorFlow GPU backend, and we trained the filtering CNN by extracting patches, obviously, because it's like you need enough training data to train the network. And then we used the learning decay. So initially we started off with the learning rate of 10 to the power minus 3, but then as the network got like through the later stages of training, we like reduced the learning rate because we needed that stable training, that's why. And then we use the larger batch size for, again, the stability. So this is an example of the raw coherence that I was talking of. So if you just compute the complex correlation, you would get something like this, but this is not really much useful because it's extremely grainy. So when you do the MRF-based thresholding, you get the image on the right. So the image on the right is actually the training target. So this is a comparison with other methods. So the first image you see here, this one is the input. So this is the phase that is captured by the satellite. The difference between two successive images of the same place. As you can see, it's like a lot more, it has a lot of noise, these stripes. So as it turns out, these stripes are actually the steps of the mine. So because the signal reflects in different ways from the steps, that's why you get this kind of grainy structures. So this thing is the result of the boxcar, that is the earliest method. And I think I should point out one thing, that because we are comparing a method that's running on the GPU, because like obviously it's a network. So these other methods also were implemented on the GPU, because otherwise you can't do a fair comparison of the time. So the third one is the NL InSAR, and it's one of the recent methods, I think around 2014 or 2015. This one is the result of the NL SAR method. This is also pretty recent. And then finally, this is the proposed method. So the thing that I'm trying to say here is that like it gets something that's pretty close in quality to the like pretty recent methods, but it does it in a much lesser amount of time. So these are the quantitative results. You see the same methods, and we use the three metrics: accuracy, precision, and recall. And mostly, it can be seen that the method is doing better than even the recent ones, and the time is obviously a lot lesser. So in a general evaluation of the method with compared to the other ones, is that compared to the boxcar and NLSAR, it actually gets a better demarcation between the coherent and the incoherent regions. And this is one of the requirements of the InSAR processing pipeline. Also, like the number of coherence misclassifications is comparatively less. Obviously, like we are not experts in InSAR, so we sent our results to the company, and then there are people in the company that have like 10-15 years of experience with InSAR, and they would tell us like what is the strengths and weaknesses of our method with compared to the other ones. So then we don't have the image border artifacts. That is another. The third thing is we can actually tune the smoothness parameter, the alpha that you saw in the MRF thresholding. Then yeah, so one weakness of our method is it still relies on the coherence computation, like the raw coherence computation, and there's an inherent bias in that. So we can actually do more experiments to see how we can further lower that bias. So one thing that the bias depends on is what is the size of the window that you're using to compute the initial the raw coherence estimates. So execution time is obviously a strength for our method, and in general the quantitative and the qualitative results show that our method is able to get a similar performance as the state of art, but at a much lesser amount of time. Yeah, so the main point of improvement is the bias in the raw coherence, and the main strength is the speed. And in general, this we can see from this research that there is some promise of using CNNs to do the InSAR coherence classification. These are the references, and that's pretty much it for me. Questions? Thanks for listening. Oh, by the way, so 3V Geomatics is the company that we were working with, and Carrick is the funding agency for this project.
Any questions?
Hi.
Did you consider doing the training the networks on the image before you did the interference?
Okay, so no.
Image to smooth, you want to get rid of the noise, denoise it before you did the interferometer?
No, I think the stage at which we got the interferograms from the company, they already passed through those initial stages. So we had to work on that. I'm sorry, what?
Repeat the question.
Oh, okay. So I think the question was before doing the interferometry, did we try denoising the images?
Yeah.
Yeah.
I've seen recently they've done a lot of denoising for rendering programs for Blender and stuff. NVIDIA recently put out a denoising AI filter, and so it seemed quite familiar. And they're doing it before they do any kind of other processing. I just wondered if that was familiar to you. Have you seen the NVIDIA stuff for rendering?
No, not really. Not really.
Regarding your alpha parameter, it's you want to fine-tune the alpha parameter with respect to smoothing, right? Smoothing the image.
Yeah, yeah. So yeah.
So how is there a specific method that you used to choose set your alpha parameter?
Yeah, it's we tried different values, and then we sent the results to the company, and they said what's best for them. Yeah. So it's experimentally, we didn't use any formula and say that this is the best bet.
With your images, compared to yours, can you estimate how the volume of the land which was moved from the mine?
I think, there are definitely some physical models that the company has that can do that, But just using this network, no. So this is just all operating at the denoising phase of the pipeline. So there are like 3-4 other phases, and then finally you can estimate a lot of parameters like motion rate, then height error, and I'm sure like the one you mentioned might be also one of them.
For those other methods, like you showed the time difference, but
Yeah.
how long does it take to train a boxcar method?
I don't think the boxcar needs any training at all.
So there's no training time
Yeah.
compared to how long would it take to train the CNN?
For us, but yeah, the training is just one time. So during the
But then
prediction,
for each different data set, you would need to train it. While for boxcar, you don't.
I'm sorry, for each different what?
For each different type of data that you get, you need
Oh,
to
okay,
train
okay.
it on the trip.
No. So the idea is like when the company actually implements it, so they'll have like a big data set that has different types of interferograms from different minings, and maybe that training might even take like 2-3 days. But that's it. Like once it freezes, they use that network. So the runtime is only for the prediction that's on the GPU, and that's the same.
Okay. Thank you.
Yeah.